Hello, welcome back. Happy Friday. So today we're going to look at, we're done with categorical data. I hope you enjoyed looking at the Titanic. That was a lot of fun for me as well. That was categorical data. Now we're going to look at the other type of data that we have, which are quantitative data. So quantitative data, they have units, they're usually numbers. They usually have units, but they don't necessarily have to be. So for instance, let's say that we're interested in earthquakes. So back in 2011, there was a really devastating earthquake that hit the coast of Japan that almost destroyed a nuclear power plant, almost melted down. That earthquake was a 9 on the Richter scale. And let's say that we wanted to know more about earthquakes. For instance, is a 9 that unusual for an earthquake to have a Richter scale of 9? So one of the first things we would want to do is we'd actually want to graph out all of the data that we had on earthquakes and their magnitudes. So when we want to look at that, one of the easiest ways that we would graph that out is to look at a histogram. So a histogram differs, it looks pretty similar to a bar chart, but it differs because bar charts are used for categorical data, where histograms are used for quantitative data. One of the differences you might notice between them is in categorical data with bar charts, we have gaps in between the actual bars. These gaps are telling us that these bars are not related to each other. Now, when we had side-by-side bar charts, when we were graphing, let's say, male and female for first class or something like that, those two were related to each other, so we would actually make them touching. But then the different categories like first, second, third class, those would have gaps in between them. Okay. Also, if we graph the survival and the death rate for first class, those two are related, so they would be touching, but then there would be a gap between the survival and death rate between second class and first class. Okay, so in a histogram, all of the bins are going to be touching each other because they're all related. There's no spaces in between them. Also, if you notice down here, instead of having our categories or our bins that we're mixing or putting them in, now we have a scale of our quantity of our variable with its units of magnitude for the Richter scale. Another thing I'll point out is when we're dealing with bar charts, the order doesn't necessarily matter. You might think naturally it makes sense to do first, second, third class, and then crew after them, but we could move this around and switch it up, and it wouldn't make a difference. However, when we're dealing with histograms, the order is very clear. We're dealing with a number scale going from small to large, and we have our units here. So what ends up happening with the histogram is we basically take our quantitative data and we break it down into certain bins. Now, kind of like a category where we're just saying it's a range of values. So for instance, from here we can read that the highest or the most common size earthquakes are going to be anywhere from a 7 to a 7 point. Well, I don't know. How big or how wide is this bin? Well, to figure that out, as you can imagine, so we're going to go from 7 to 8. We're going to count the number of bins. 1, 2, 3, 4, 5. So 1 divided by 5 is going to be 0.2. So this is going to be from 7 to 7.2, but not including 7.2. 7.2 would actually go into the next bin. Okay, so anywhere from 7 to just under 7.2. So the most common, the mode, which is the most common magnitude of an earthquake, is anywhere from 7 to 7 point up to 7.2. And if we look on from the 9, which was the earthquake that hit Japan, that was a 9. And if we look over here, 9 would be the highest earthquake that we had recorded. And this data actually the book was going into, I believe they said it was data of several thousand earthquakes that we've had from all the way earthquakes we had recorded and estimated their size from several even thousands of years before BC as well. So lots of data that we had on earthquakes, and that would have been a very unusual earthquake. So one of the largest ones that we've had in recent history. And of all of history since we've been recording them, it would have been. So a very, very unusual earthquake that hit Japan. Very, very unusual magnitude. Okay, so that's a histogram. So just kind of breaking down histograms here, we use histograms for larger sets of data. We're also going to talk about stem and leaf plots and dot plots. which we use those if we have smaller sets of data and we can actually show all the individual datum. But if we have like thousands of earthquakes that we are trying to summarize, we don't want to see the data for all 1,000. We just want to stack them up in bins where we can read the magnitude and the size of the bins. Okay, so it's used for larger sets of data. Smaller sets of data, we can actually preserve the datum itself so that you can see each individual piece of data, but that would be overwhelming in a histogram, so we don't use it. Flexible bin intervals, so we could change this. We could spread out these bin intervals, or we can crunch them up together and they kind of end up stacking up. In this case, our bin intervals is 0.2. If we would have had bin intervals of just imagine what it would look like if the bin interval was 1. So all of this data would all be stacked up in one bin. All of this would be stacked up in another bin. All of it between 7 and 8 would be stacked up in a really big bin, and then a smaller bin here. So the smaller we make our bin size, the more detail we are able to see between all of them. So you don't want your bin sizes to be too big. In this case, the size of bin size of 1 would be kind of unusual. Would be very helpful either to see what's actually going on. So histograms also don't display the individual data. Whenever we get to a stem and leaf, let me show you that real quick. So here's a stem and leaf. So the stem tells you, well, there's a key here, right? So the bar separates between the 8 and 8 would mean 88 beats per minute. So 8 and 0 would be 80 beats per minute. 8 and the 4 would mean that 2 people or 2 students had it at a resting heart rate of 84 beats per minute. So you can actually tell all the individual data whenever you're looking at a stem and leaf plot. You can see all the individual data. So if we have smaller data sizes like 15 or 40, it's just a general rule, then we could actually show the data. But and you see the exact same data over here. If I flip this, let me see if I can flip this left and right and then rotate it here. Does that look familiar? That's the exact same data we have over here. And you can see the small part, the longest part, and then all those are equal in here. So a histogram gives us the same shape. The only difference is that it doesn't preserve the actual data points. You see that? So it's all blocked out. We don't know where those are ranging in those values or the actual values themselves. We just know the general shape from a histogram. That's why we use histograms for larger sets of data, because we couldn't see all those data if we were talking about the data, like thousands of earthquakes that we have data for. All right, good for comparing multiple distributions when the scales are equal. Yeah, so if we're comparing this distribution to another one, we just want to make sure that we don't stretch one of them out and that we keep the scales the exact same. Otherwise, it would get kind of difficult to interpret. So as long as your scales are equal in the vertical and the horizontal, you can compare histograms, multiple distributions together, which is good. And if there are any gaps, you can have gaps in the bars, but not in the bins. So basically, you need to keep the bin sizes consistent as you go. Don't like skip and go from 5 and then make this one 3 instead of 4 or something like that. So make sure that you keep that all the way consistent. Yeah, see fewer notifications. Anyway, so make sure you keep that all consistent, and you should have gaps in the bins, in the bars, but not in the bins. So here you see that there were not any earthquakes that were from anywhere from a 3.8 all the way up to maybe about a 4.2 or 4.4. Looks like that would be, yeah, 4.4. Anyway, so there is a gap there. There weren't any recorded ones, and it's okay to have gaps in the bars themselves, but not in the bins. Just make sure your bins are consistent as you're going and your scale across. All right, sometimes with histograms we can do relative frequency histograms. So if you look at our Y scale here for our response variable, this is measuring the number of earthquakes. So it looks like we had, I don't know, about 230 earthquakes that were magnitude of anywhere from 7 to 7.2, but not including 7.2. Sometimes we might change that to a relative frequency. If you remember relative, we just changed it to a percentage. So that would tell us that the overall percentage was about 18% of all earthquakes were at the largest bin size, which was anywhere from 7 to 7.2, but not including 7.2. Okay, and whenever we change that, notice that it's the exact same histogram. Nothing changed in the histogram. The scale, the horizontal scale is exactly the same. The only thing changed is the vertical scale. And the way we actually changed the vertical scales, we actually divided it by the total number of earthquakes. then multiply it by 100 if we were not writing it as a decimal, but rather percentages. But essentially that's what you're doing. So sometimes that's helpful, and we have relative frequency histograms. So let's see if we can interpret the histogram over here. So this histogram came from a random sample. They looked at a page and they randomly sampled words from 30 randomly sampled sentences from our textbook, and they were looking at the number of words that were in a sentence. So just this is a way they actually they try to judge reading levels. So books with a harder reading level are going to have longer sentences in them. So anyway, it's kind of a way that they do it. So something that they're interested, the publishers are interested in. So the first question we have is, what percentage of these sentences contained anywhere from 5 to 9 words? So we got to find the bin that corresponds with 5 to 9. So the 5 here would actually be included in the bin to the right of it. So this is going to go anywhere from 0 up to 4, but not including 5. And this one would be 5 up to 10, but not including 10. So this is the 5 to 9 bin. And it looks like that's going to be in a percentage. This is relative frequency histogram. It looks like it's something like 16.5% of all of those sentences contained anywhere from 5 to 9 words. What about 25 to 29? So 25 to 29 goes up to 30, but not including 30. That looks like that's about 13%. 10 to 19, so 10 all the way to 19. That's going to include 2 bins. So all we would do is add those percentages together. So 13% plus 33%, that's going to put us at 46% altogether. So 46% was in one of those 2 bins. Fewer than 15 words, so up to 15 but not including it, so that's not going to be in this one. So we can add those 3 together. So that's going to be 3 plus another, we'll just call that one 16. So that'll be 19 plus another 13. So that's going to be 32. So 32% are all under 15 words. All right, no big deal. How many of them contained anywhere from 20 to 24? So that's this bin here, which is 20%. More than 25 words, so 25 or more, that's going to be this bin right here, which we said was about 13%. All right, so what is the mode or modal interval? Okay, so the mode is simply talking about the most frequent bin or interval or bin size. So our most frequent one is going to be anywhere from 15 to 20, but not including 20. By the way, this is how you would write it out in interval notation. So the first bin here goes from 0 to 5, but not including 5. So strictly less than 5. All right, so we already kind of talked about stem and leaf plots, but they're used for smaller data sets when we can actually preserve the data values themselves, which would be kind of nice. We're going to break down some of our data that we gathered in our survey that I sent out at the very beginning, and you'll actually see your specific data. You'll see where you were in the whole thing. So I think you guys will enjoy that. So the stem, you have to have a scale or a key that goes with a stem and leaf plot. So this will tell you this is the tenths place. These are the ones place for beats per minute, and also gives you your units as well. So stem and leaf. All right, dot plots are similar to a stem and leaf plot, except they don't actually preserve the actual data values, but they do have 1 dot for each data. So they're not as preferred to a stem and leaf plot, but if you want to still give the general shape, just like a histogram, but you don't want to see the actual data to distract people or something like that, dot plots can work. Because dot plots don't show the actual numbers, you can use them with slightly larger sizes of data. Before you just want to start using a histogram. If we had like 2,000 dots spread out across here for the earthquakes, it would look really, really busy. So at that point, you just use a histogram. So you have 1 dot per datum. They can be horizontal or vertical. So just kind of like you saw, like I showed earlier, you can display dot plots horizontally, or you can do it vertically. Same thing with a stem and leaf plot. Doesn't really matter. Histograms are usually only shown horizontally that I've seen. All right, so we're going to talk about ways to describe distributions. We describe distributions by their shape, their center, their spread, and their unusual features. So first, we're going to talk about shape. So this is talking about the mode. So unimodal, bimodal, multimodal, and uniform. So the mode, again, talks about the most frequent. So what is the most commonly occurring bin? In this case, unimodal histogram has 1 clear mode. So it has 1 peak, kind of just like a mountain that goes up and it goes down. It's got 1 clear peak. And then bimodal, this one has 2 clear peaks. And there's lots of examples of reasons why we would have binomial distributions. And so this is actually pretty common. Multimodal can have multiple modes, like you can see here, it has multiple peaks. And then uniform is pretty well straight across the board. So anyway, yeah, uniform. It doesn't have to be exactly uniform, but if it looks pretty evenly distributed across the board, then we would say that it would be uniform. There's no real clear mode. The next thing is when we have something that's unimodal, we also might say that the distribution is unimodal and symmetric. So symmetric just simply means if we reverse it, or like fold it in half and fold it over on itself, how well does it line up with itself? So if it's symmetrical, then the left side will look similar to the right side. So it'll fold over and it'll match up really nice. If it's not symmetrical, then we say that it's skewed. The data is skewed. So these two are both unimodal. There's one clear mode on both of them, right? But they are skewed. So this is looking at the number of cardiac patients, female cardiac patients, for a heart attack or something like that. And so if we're looking at their age, as we would expect, most of the female cardiac heart attack patients are going to be in their 70s or late 60s or young 80s or something like that. But you are going to have some that have those issues when they're really, really young, and they're apparently in their 30s. But at a certain point, you're not going to have 120-year-olds that are still having heart attacks, because we usually don't have people living up to 120 years old, right? So this data would naturally be skewed to the left by the younger people. And we'll talk about what happens to the mean whenever we have data that skews the mean. It's actually going to pull the mean over to the left. But we're not going to talk about mean until we get back for next week. So anyway, also you'd have skewed to the right. So how much do they charge those patients? Well, most of the patients had a smaller charge. We're talking about 10 grand. That's a lot of money. But anyway, a smaller charge. But some of them had extended stays because of complications with the heart attack or something like that. And so their bills could rack up almost without end, right? But you can't have a bill that's going to be less than $0. So you have this hard left bound here. So naturally, this data would be skewed to the right by extreme circumstances where, I don't know, somebody ended up staying in the hospital for a really long time. So if you want to remember the difference between how to describe something that's skewed to the left and something that's skewed to the right, just follow the tail. So the tail on this one clearly goes to the left, and the tail on this one clearly goes to the right. And that's how you can remember how to describe unimodal data that's either skewed to the left or skewed to the right. Sometimes you have some unusual features that can come up, like outliers. Most of our data is all packed together, and then there's several gaps, and then over here we had some data. Something happened. So this sometimes whenever we have outliers, it could be an error in a data entry or something like that. But if we have a large gap where it's very obvious, kind of out on its own, that could be considered an outlier. We will discover how to calculate outliers mathematically with a fence test or with z-scores on Tuesday when we come back, okay? All right, the other thing is gaps. So if we have like a group of data, then we have several bins that are empty, and then another group of data, then we would consider that a gap. So if we just had one that was missing, like one here, that's not necessarily considered a gap. It could just be our sample size is so small there just wasn't anyone in that category or in that bin size, and if we increase our sample size, naturally it would get filled in, okay? So it takes several empty bins in order to call it a clear gap in the data. And also notice that these are not considered outliers because they're all grouped together, right? This one's out by itself. That would be considered an outlier. But when we have gaps between the data where we have several on one side and several further away and there's nothing in between them, that's considered a gap, okay? Kind of obvious, but I thought I'd point out. All right, so this is your data that we gathered. This is the plot of the number of siblings. So mine is the red X here, so I just add myself to the data. So I have 6 siblings, so there are seven children altogether. One of you guys has 10 siblings, so I guess 11 in your family plus your parents or whatever. That's a big family. I think that was the biggest one that we've had last year. I don't think we had anyone that had a family that large. What's interesting, there's only one person who's an only child. So most of you guys, if we see here our mode, most of you have one other sibling. And then for some reason, not as many had 2 siblings. And then again, looks like we have another mode. So this would be bimodal data. You might consider that, where people either had 1 sibling or they had 3 siblings. Kind of odd how that worked out. Also, we might describe this data as being skewed. It's skewed obviously to the right? It's impossible to have less than 0 siblings, but it's always possible to have more siblings, right? And so naturally our data would be skewed to the right. Also, this is a dot plot, even though we're using X's. We can't see the actual data, but we do know what the actual data is because there's not multiple bins in there. So it's not like you could have 1.5 siblings or something. These are all integers. It's 0, 0, 1, 2, 3, 4. So anyway, it's a dot plot. We actually do have the actual data preserved. There was no reason to do a stem and leaf because we weren't combining several into one bin. We were able to spread it all out just because of the nature of it. So I thought that was kind of interesting. The only other thing we have to do with describing a distribution is the center and the spread. So whether we use the median or if we use the mean and interquartile range, or the median and the mean and standard deviation are the two options that we have. We're going to get into those next week, so hold tight. Next question is, how many states have you visited? And this is actually on your homework assignment. So if you want to go ahead, it's the top of the back page. So I went ahead and put out all that data. This is another question that I asked you guys in our survey. So counting the number of states that you visited. I think some of you guys said that you hadn't visited any states. So, but it's kind of, you've clearly visited Oklahoma. So I decided to interpret that as you've actually visited one state, which is Oklahoma. But we didn't necessarily clarify that. Kind of the same thing that we could talk about with the number of siblings. Are you counting yourself as a sibling? Well, we said that 0 would be an only child, and so I'm guessing that 1 would be that you haven't visited any states except for, of course, Oklahoma, where we currently are. Okay, so how many states did you visit? Let's look at that data. So I've actually already organized this data into 2 different bin sizes. So these are clearly going to be stem and leaf plots. So this is the 0s and 0s for the tens positions, and then 1 and 1 for for 10. So and then up to 20. All right, and then so the rest of all of this is going to be the leafs. So it looks like we had 3 people that had visited one state. So have never been out of the state. I'm interpreting it that way. 3 people that visited 2 states. Looks like 5 that visited 3, 4 that visited 4, and et cetera, et cetera. You can read. And then once we get to here, that's 2 of them that had 10 states, 1 that was 12, 17, and 1 person who had visited 20 states. So if we did a bin size of 5, and I'll ask you to make your own, so you can look at that. Also, if we change it to a bin size of 2, now it takes 5 of these, because if we're doing 10 divided by 2 would be 5, so it takes 5 of these. So this first bin is going to be 0 and 1, and then 2 and 3, 4 and 5, 6 and 7, 8 and 9, and then we're up to 10, which would be 10 and 11, 12, 13, 14, 15, 16, 17, 18, 19, and this one is 20 to 21. So anyway, what I do want to draw your attention to is the contrast between what happens when we have large bin sizes, like bin size of 5, and a smaller bin size, like bin size of 2. So when we have, technically these are both correct, but when we have a smaller bin size, it spreads the data out so that we can see more detail. Instead of stacking all of them up together, this spreads it out so we can see really what's kind of going on. There wouldn't be much use to really spread out even more to bin size of 1, kind of like we did with the number of siblings. You could, but at some point you kind of want to group things together so it's not too wide. So next thing we want to do is figure out how to create a histogram. So I'm going to show you how we put this in the calculator. Usually you guys would have calculators by now. If you already have a TI-84, that's awesome. You can follow along here. You do have kind of a printout of how we go through this, and you can go back and watch the video, but we do need to start practicing using the calculators. We ordered some extras so that we will have enough for me to give them out this year. We just haven't, Stinnett has not gotten back to me about when we're going to do that, but I will definitely I'll let you guys know as soon as we know, and we'll be able to pick up the calculators and textbooks from the school. So another thing is, you also, if you don't have a TI-84, you might be able to get an emulator. I hear there's emulators on the iPhone, and there's definitely emulators for Android. So if you want to get an emulator for a TI-84, it might get you by until you can get the actual one in your hand. Okay, so what we're going to do is we're going to hit the Stat button. We have our own button. How nice is that? And then we're going to go to Edit, so we're going to hit Enter, and we're going to input our data. So in List 1, we're going to input all of the individual data. So there's 27 of those altogether. And if you look at the very bottom of the screen, it'll tell you for List 1, this is the 27th the 27th data, and so that's going to be number 20. And if we go down to the one below, it's 28. So that tells us that we didn't miss any. We got all 27 of our data. And then in list 2, we can also write this out as a frequency table. So how many did we have that had 1? Well, we had 3 of them. So we'll put 1 in list 2, and the frequency would be 3. We had 3 that had visited 2, and then we had 5 that visited 3. So you can see how the frequency table works. Make sure you line those up, because if it gets off, then it's going to throw off everything. And there was only one person that had these down here. What is nice about doing a frequency table, especially if you have large data sets, is you don't have as much that you have to put in the calculator. Like compared to this one over here, there's quite a lot less that we were having to put in the calculator because we did a frequency table. So that is preferred with larger data sets. All right, next thing we want to do is we want to display a histogram. So instead of going to the y equals plot, we're going to go second y equals. And if you see right above that in blue, it says stat plot. And we have 3 different plots we can use. We can also go all the way down here to turn them all off or turn them all on. So right now I have plot 1 that's on. So I'm going to hit enter. And it is on. You can also get to your different plots by arrowing up over there. So anyway, those are off, so it doesn't matter. So I'm going to go to plot 1. The type, we're going to do the histogram, which is the third one. We will know what all those are by the time we're done here. Not today, but with this unit we will. Then our X list. The X list is where where all of our data is, and we put it all in list 1. And so if you look above 1, there's the L1, which is in blue. So we have to hit second 1. Okay, and then the frequency, because we're not using a frequency table, we don't use a second list for that one, so we're just going to leave it as 1. So for each data that we had in list 1, which was all of them, they all have a frequency of 1. So it's just kind of weighting those, no big deal. And then the next thing we want to do to actually graph it out, if we hit graph, it's going to graph it over a y-axis, which is not what we're really interested in the Cartesian plane. It looks pretty gross. So what we have to do is hit zoom, and there's a special option for zoom. Zoom 9 is zoom stat. So it zooms in for the statistics plot that you're trying to graph. So zoom 9, we'll be using that quite often. And there you go. There's our histogram, which looks fairly similar to what I've already got here, except the problem is it's going to have a funky window. So what we want to do is we want to go to the window, and for our minimum we're going to do 1, maximum we're going to match this this window here, which is a bin size of 2. So we're going to do a maximum of 22. Our X scale is going to be, we're going to go by 2s for our X scales. That's our bin size, right? Actually, we're going to start our minimum. We're going to start it at 0. Then our Y scale is not nearly as important. We can leave whatever it defaulted to. That would be totally fine. Okay, and then once we're done with that, we can just hit graph. And then we should have exactly the same. It should look exactly the same as the histogram that I have here. And then you can also hit trace, and it'll tell you the max and the min for the bin. So 0 to 2, we had 3 people, which sure enough, 0 to 2, we had 3. Arrow over, we had 8 people that were in the bin from 2 to 4, but not including 4. And just keep on going over, and you got all of your data there. And several, we got several bins that had no one in it. The other thing that I want to point out here is that the stem and leaf plot data is the exact same distribution and exact same shape as our histogram. So what's the difference between the histogram and the stem and leaf? Well, the stem and leaf preserves the actual data. The histogram just gives you a general summary, and we usually use histograms for larger sets of data. Now there's one other way you could have put this in the calculator. So I'm going to go back to second stat plot, and I'm going to turn on a second plot here. So I'm going to go to plot 2, I'm going to turn it on, go over to the histogram. Okay, and for this one, I'm going to do X list. This time I'm going to use my frequency list, which was list 2 and list 3. So list 2 is going to tell us the actual data, and then the frequency for the data in list 2 is in list 3. So second 3, that's the list 2 and the list 3, okay? And then I'm going to hit graph again, and you'll notice it graphed the exact same histogram, but this time it's a different color. So what that was using, I'm going to go zoom in, it was using list 2, and its frequency list was list 3. instead of just using list 1 with a frequency of 1. So anyway, you can do it several different ways, and that's how that would look. And that's pretty much it. So you got the rest of the back, just a few more problems to do on your own. Again, if you're having any questions, go ahead and message me in the private comments in Google Classroom, and I'll get back to you as soon as I can. I've got all the solutions typed up. I just have to copy and paste them over to you. Eventually, you guys will have the textbook, so you can check your answers in the back of the book with the odd problems. But if you are having any problems or any questions, the easiest way is just to go straight to me and to ask that question. So hope you guys have a good 3-day weekend, and we'll come back and I'll see you guys on Tuesday.